Good morning. We are going to see something very interesting today. We're going to see how, given the system, we can get CAMG to do a computer-generated transfer functions. So we have just the system, and what we need to do is to create a bond graph model of this, and then show you how CAMG actually can generate any transfer functions of this. Maybe if simultaneously we can create two transfer functions. So in this case, we need to define what the outputs are and set up the objective, what the transfer functions are, and then we'll go from there. So I will disappear now. And the first thing we're going to do is, like I said, let's set up our objective. Objective, you could say, find the transfer functions for the voltage C in relationship to the input V. This is our transfer function 1. And the second one we want is the voltage on the resistor in relationship to the input voltage. And we're going to call it transfer function number 2. Okay? This is what we're after. So I think what we need to do first is to build a bond graph model on the system over here, and then we can create that bond graph model and go on to generate the transfer functions. One thing that occurs to me is I'm just going to change colors here and do something a little different here. Why don't we just draw the bond graph model right on the system, on the circuit? And let's say, okay, this is a 1 in here for for I1. This is a 1 in here for I sub 2. And then, as the step says, put the elements attached to that. In here you have this voltage SE right there, which is this one. Attached to this, we have the R element over here, this one. And attached to this, you have the I element, which is this one over here. And in between these two, you have the C. So you see we have been able to draw the bond graph right on the circuit itself. There you go. And this is the blue bond graph is what we will enter into the into CAMG. So let's do that right now. So we go over here and we say, okay, then let's go to the CAMG software over here and then do CAMG window. And then we're going to go, this is the bond graph model of the circuit as you see here. I had worked it out and entered it into it so that you can see that we have the same thing, see? So you have the SC over here, 1, the R, and then C, and then the I element over here. I don't think that would be any problem reproducing this bond graph for everybody who is listening to this, since we have had prior lectures on how to enter that bond graph into the CAMG software. One thing that I think is worth mentioning is the blue bond graph that I have in there on the left-hand side is all I need to have the completed bond graph on the right-hand side, meaning that CAMG will assign the bond numbers and will assign also the causal forms. Okay, so my job right now boils down to finding the outputs for this, defining what the output is. And the output, the voltage on the capacitor is obviously E4, and the voltage on the resistor is E2. So let's just, maybe I'll have a record of the Von Graph model in here and put it in the notes in here so that we know what we're working on. Let me just move this a little bit so that we can actually put it in here. Huh? I'm just gonna put it right here and make sure that my notes reflect um, what we have actually done so far. So this output in here, this relationship B sub C is going to be equal to E sub 4, and then B sub R is going to be E sub 2. So the transfer function number 1 is going to be E sub 4 in relationship to E1, which is the, I would want to put the SE1. This is equal to transfer function number 1. And this one here, E sub 2, in relationship to SE1, is going to be my transfer function number 2. Okay? So once we have this, I'll just go over here and I go to the interface of this and click, and I say I want to go to MATLAB, and the two programs will negotiate an interface, and I am about to specify the outputs, in this case E sub 4 and E sub 2, to be able to obtain the transfer functions. So what of all these files that CAMG generates, the symbolic file CAMG-SYM is the one that I am using for this purpose. So what I am going to do is here to say find E sub 4, which is my first output over here. And in here, E4 has already been, the equations for E4 have been derived because CAMG generates the equations for all the E's and F's on the Von Graph model. But since it doesn't know which one are the output, it puts them into like comments. So I find E sub 4 and I uncommented that, and then I define it as the first output, and then I put one here to define the first row of the C and the D matrix. Because we have another input, which is E2, no, sorry, I meant to move over here. When it's E2, then we have, no, what did I do? E sub 2 is what I want. So there we go. Again, we'll prepare this and then do this number 2 like that. And this is going to be defined this right here. Okay, very good. And in here, I am going to run this file and watch what CAMG does. CAMG MATLAB. This is the A matrix that defined in symbolic form. You have the B matrix, the C and the D matrix. It is a 2-row matrix because we have 2 outputs. And then in here, it will give you the transfer functions. This is the first one, and this is going to be the second one. So what I'm going to do is, I would like a little better in the expression for the second one. So I'm just going to use just a command in MATLAB that's called pretty, and so that we can actually the vector H is the one that in CAMG produces the transfer functions, and have them in this form, which is a little nicer, because we have in polynomial form in here and the numerator, as well as in polynomial form in the denominator. When CamG and MATLAB do their handshake, it can come out in a different format, but it's the same transfer functions. And because we like to see the coefficients, I think it's nicer to put it in this form. So I think what we're going to do is I am going to take this and put it in the notes so that you can see from CamG what is that we got. We got in here that this transfer function, what you have in here is transfer function number 1. At the top, this one right here, let me see, this one is in reality is E sub 4 in relationship to SE1, which is the same thing as we could say voltage C in relationship to V. And this is, of course, we have defined this as transfer function number 1. The second one, this one, it is this E2 and divided by SE1. And this is what we have defined as voltage of the resistor divided by this as transfer function number 2. Okay? So now we have the two transfer functions, E2, which is the voltage C, and E4, which is the voltage VC, and we have the other transfer function for E sub 2 divided by the input, which is voltage V sub R over V. So CamG has done this computer-generated transfer functions and has, as indicated in here, the coefficient and the S squared here, the coefficient of S over here, and the term. Same thing at the top. Now, what I think is it would be really helpful is to understand in reality how this happened. And the way we do that is we go back to our file that generated this. And let me just go over with you for a little bit what you have in here. This CamGSYM file. It has the definitions of what the inputs vectors are in here and what the state variable vectors are in here. And then it derives the equations. You see, there is the differential equations in here and calculates the A and B matrices. When you do this, when you define this is E sub 4 as one of the outputs, CamG generates the first row of the C and the D matrix. And when you define the second one right here, it generates the second row of the C and the D matrix. Then after done that, it just displays the matrices right here. That's what this is doing. And then watch this, comes down here, calculates the Si minus A matrix, and watch that. That is the same operations that we did just on the prior explanation on how to get any transfer function. Do you see? So it's taking advantage completely of the state space form and the fact that using the matrices we can obtain any transfer function. The thing I like to add is that it's doing it symbolically, and this operation that you see highlighted in there is going through the symbolic toolbox of MATLAB. And that's how we obtain this, this statement that says pretty H is the one that produces the transfer function, the display that you saw before, the one that you have in here, see right here. I made it so that it will display it even more pretty, so that we can actually see it really well. But I think that's in essence what's happening. And that's the application of what I have mentioned a little earlier of use of obtaining any transfer function. If you know the state space form, you can use this to obtain any transfer function. Here we obtain two. We could have obtained one or we could have obtained three. It's not a problem. The only thing we have to do is define the outputs. In fact, if you would like, I think as a closing, you may say addition to the explanation here, is we could go ahead and define a third transfer function, a third output. And in the case of our circuit over here, we could figure it out. What about, you know, our output is I2. I want to know what the current I2 is. So why don't we just go down here and we say, okay, additional output. In this case, you would say it's f sub 5 or f sub 6, I2. So in here we'll say I2 is equal to, we could just say f sub 6. And so if we do that, we are here and then our filing here, we go and we use the find, and you say, okay, look, I am looking for F6. So please find me F6, there it is. And this is gonna become my third output in here. So when I set this up, I uncover the percentage signs, and this define it as the third output. This is going to be number 3, which makes the C and the D matrix expand to accommodate my new request. And then I'm just going to say run please for me, and we'll see what MATLAB is going to do. See, now the C and the D matrix, you notice they have 3 rows, and yeah, lo and behold, you have 3 transfer functions. And this one is the transfer function number 3. I think we did something to make it look pretty. I'll just do the same thing. I think we said pretty was collect terms so that it would look nice, because it looked the same thing. Yeah. I think I just did one more T and doesn't like except once it wants. And this one is the actual, you know, this would be using the third output. I'm going to go and capture this and put it in my notes. And the output for number 6 in here, let's see, let's just put it over here. In here, what you will have is, you know, the first 2 that we did are these 2. But this one right here this is f sub 6 in relationship to the input. And this is the current I sub 2 in relationship to the input. This is, in the bond graph notation, is SE1. And this is what we will call transfer function number 3. But you could find any transfer functions using that way, not by, you know, doing a lot of algebra, but just knowing a little bit on how to manipulate the setup of the ABCD matrices, which is what this lecture is about. We are using the state space form to find the transfer functions. In this case, the computer generated transfer functions. And that's the explanation on this topic.